Hey, hello, ib1 higher level students. How are you? I'm fine. Okay, so let's start a lesson about relativity. So first, in new chapter, let's write the topic nature of force. Okay, important is that I hope you watched the movie prepared by me to G9 students about magnetism. It's very important. If you didn't see it, so please stop this video, and as a revision of magnetism, please find on my channel G9 magnetism 2 about motor effect. It's very important. When you will be ready after watching, please back to this movie. Okay, so as a revision, we have to do 3 things with it in middle school. It's also very important to understand this. It's crucial for this topic. First of all, I hope you remember Coulomb's law about interaction between 2 charges. Okay, let's imagine that you have 2-point charges, positive and negative, which interacts. Of course, you know that there is a force of interaction called electric force, and charge number 1 in this case repels charge number 2, and charge number 2 repels charge number 1 by force of the same value but opposite direction. Mathematically, we can write that Coulomb's law is about interaction, and that force between 2-point charges is equal to the constant called Coulomb's constant, charge 1 times charge 2, of course charge 1 is charge of first, charge 2 is charge of second, divided by squared distance between these point charges. Okay, so basically force of interaction between charges is proportional to the charges and inversely proportional to the squared distance between them, and this K, coefficient of proportionality, is called Coulomb's constant and is equal 8.99 times 10 to the power of 9 standard units. So in this case it will be Newton times squared meter divided by Coulomb's squared. Okay, so please note this in your notebook. Let's write point number 1, revision, and bullet point number 1, Coulomb's law. Okay, about interaction between charges, electric interaction between charges. I hope you are prepared. You have your book, notebook, you have pen, pencil, a ruler, eventually calculator. Yes, it's normal classical lesson. Okay, so nature of force is a topic, and point number 1, revision, and bullet point number 1, Coulomb's law. And please copy this. Okay, second, you have to remember from your middle school is a fact that each moving charge creates a magnetic field around. Okay, so moving charge creates magnetic field around. Okay, so let's imagine that you have charge which moves along a vertical line. So it's a 3D picture, so I'm going to create a plane through which this line passes. Okay, this is a line along which this charge moves, and let's imagine that our charge is positive. Yes, so charge travels from lower part of the screen to upper part of the screen and passes through this plane which is perpendicular. Okay, how to find magnetic field created around this charge? You can use right thumb rule. I hope that you remember this. You have to take your right thumb. Let me try to draw. I'm right-handed, so it's difficult to me. Yeah. Okay, sorry, on the ordinary board it's better, yeah? Okay, so this is your thumb. Thumb indicates direction of motion of charge. I'm talking about positive charge. Here we have nails, yes? Okay, so thumb indicates direction of motion of charge, so our charge travels along this line. Okay, and fingers show us what is a direction of the field. So field is around in the form of circles. So magnetic field lines are around in the form of circles, and direction can be found by using right thumb rule. Is it clear? Of course, if you have a negative charge, then situation is completely opposite. So positive charge, right thumb, okay, for negative charge there is an opposite direction, okay? So left hand or right hand and invert this. Okay, so we did this in middle school. I hope you remember this. It's very, very, very important. Okay, and third point about revision is related with the fact that if charge enters the region of magnetic field, yes, then magnetic force acts. So if charge enters the region of magnetic field, then magnetic force acts. Okay, so let's look also in 3D. Let's imagine that you have a magnet. North pole is here, south pole is here. Of course, magnetic field is directed always from north to south, so from N to S. Okay, and let's imagine that you have a charge, a positive charge, again positive charge, which travels along this line and enters this field here. Okay, so what happens? You can use left hand FBI rule. Okay, like this and like this. Not bad, but should be better, yeah? Okay, and left hand FBI rule says that due to the left hand FBI rule, you can state direction of this magnetic force, because magnetic force is always perpendicular to the direction of motion. Okay, and depends on the orientation of direction of motion due to the field lines. Is the biggest if charge enters the field perpendicularly, and doesn't exist when charge enters the field along field lines. Okay, so what happens when this charge enters the field here? Okay, due to the Fleming's left hand rule or left hand FBI rule, we have that first finger shows direction of field which is directed to the right. Okay, middle finger shows direction of motion which is towards the screen, and thumb indicates direction of magnetic force. Okay, so magnetic force in this case acts down, making a path in the magnetic field, making a path circular. Okay, so our charge changes direction of motion, moves on the circle, because magnetic force is always perpendicular to the direction of motion. So when direction of motion changes, then of course also direction of magnetic force changes. Of course, if you have a negative charge which enters the field, we have the same situation, but the direction of action of force is opposite. So in the case of negative charge, like electron, yes, you cannot use left hand rule. Oh, you can, but you must remember that finally you must invert the direction of motion. So basically, for positive charge, left hand rule, for negative charge, right hand rule. And remember, force is perpendicular to the direction of motion always, and force doesn't exist if direction of motion is along field lines, so when particle enters along the magnetic field. Okay, do 4 or 5 examples related with this is very important, and then will be more advanced example and our standard lesson. Okay, so your task is to find the direction of motion of force in first 2 examples of force. So let's imagine that magnetic field is directed to the right, and we have positive charge which moves towards the screen. This is first. And second, you have magnetic field directed up and charge which is negative enters the field to the left. Do these 2 examples, and what is the solution? In first, we have positive charge, left hand rule, we are looking for F, B is directed to the right, so first finger to the right, direction of motion is towards U, away from the screen, so middle finger away from the screen, so finally force acts up. I hope you have a correct answer. And second, B is the right hand because it's negative charge, B is directed up, V is directed, so first finger directed up, V directed to the left, so middle finger directed to the left, and F is directed towards you, so away from the screen. Okay? And 2 more examples. Yeah, 2 more examples. Now, in first you have to find B, in second you have to find V. Okay, so let's imagine that force is directed towards you. You have positive charge, and this charge moves up. And second, we know that B is directed towards the screen. Force is directed in this way. We have a negative charge, and your task is to find direction of V. Do this. Okay, so in first, positive charge, left hand, we don't know B, so we don't know what is the first finger. F is directed towards you, so thumb towards you, middle finger up, so I have F directed to the left. B directed to the left, of course. And second, negative charge, right hand, we know F, which is directed upright. We know B towards the screen. So what is the direction of motion? Left up. I hope you did this perfectly. Okay, and one more example. Let's imagine that you have 2 long current carrying wires. Okay, in first wire we have current I1, in second we have current I2. What happens between these 2 wires? When current flows, then there is also magnetic field around the wire. Again, right thumb rule. Okay, so current one, this one, creates a magnetic field by using a right thumb rule in such way that this field goes towards you in the left part of the screen and away from you to in the right part of the wire, right thumb rule. So this is B1, B1 created by first, B1 created by first. Is it clear? Okay, and now let's focus on the second wire. Second wire, in which current flows, is placed in the magnetic field created by first wire. So we can use left hand FBI rule. Okay, left hand because this is direction of current, so the same as direction of movement of positive charge. And we can find a force. Second wire experiences a force because first wire creates a field. So what is the direction of this force? B is directed towards the screen, so first finger towards the screen, middle finger up, and force is directed to the left. What does it mean? It means that second wire is attracted by the first. and due to the Newton's third law, first must be attracted by the second. So there is interaction between wires in which currents flow. This is very, very good example, kind of, let's say, application of phenomenon. Okay, and now write point number 2, nature of force, the same as topic. It's short, but very, very important. Let's imagine that you have two charges. Charge 1, which is positive, and charge 2, which is, yes, also positive. Okay? And let's imagine that we have observer A, Alice, which observes these two charges from the laboratory. Yeah? And let's imagine that charge 1 due to the Alice moves with speed of v, and charge q due to the Alice moves also with speed of v, the same speed. And let's imagine that there is another observer. Okay, Alice will be blue, sorry. Okay, and let's imagine that there is another observer, a molecule rider, a charge rider, which is sitting on charge 1. Okay, this is Bobik. Okay, so we have two observers, A and B. And the question is, what type of force acts between these two charges in the perspective of observer A and in the perspective of observer B? Is that clear? Okay, so let's start with observer B. What does B see? Okay, from the perspective of B, charge 1, on which B is sitting, is stationary. Is it clear? And charge B, which is observed by charge 2, which is observed by observer B, is also stationary. B sees this charge always at the same position because both move with the same velocity, which means that relative velocity between charge 1 and charge 2 is equal to 0. So B doesn't see movement. Of course, B sees that A moves, but E is not important in this in the case of force between Q1 and Q2. So let's look. Due to the observer B, there is a force of repulsion between these two charges, and this force is electric force, Coulomb's force. We have no movement, so we have no creation of magnetic field. We have no movement in the magnetic field, so we have no magnetic force. So for B, this force is magnetic. Sorry, not magnetic, of course. For B, this force is electric. Is it clear? For B, this force is electric. Okay, it's very, very important. So let's write, not magnetic. Okay, let's describe the same situation from the perspective of observer A. Okay, what does A see? A, who is outside, yes, sees both charges and Q1 and Q2 moving to the right with velocity of v. Was it clear? So let's focus on first charge. When the first charge moves to the right, then there is a magnetic field around, right thumb rule. This magnetic field goes towards you in the upper side, right thumb rule, and away from you in the lower side. Away from you in the lower side. Okay, right thumb rule. So this is magnetic field created by first charge. And in this magnetic field, second charge moves. Is it clear? In this magnetic field, second charge moves. So let's take your left hand, because this charge is positive, and find the direction of magnetic force acting on this charge. We are looking for F, yeah? B is directed towards the screen, and direction of motion is to the right. So what is seen? Observer B sees magnetic force acting on the charge, yeah, which, of course, there is also electric force acting away from the charge. But the important is that observer B sees also a magnetic force. Okay, so what is the conclusion? Okay, the conclusion is that type of force or existence of magnetic force depends on the frame of reference. In one frame of reference, in observer of I was talking, this is of course observer A, because probably I've used word B at last, yes? This is observer A, of course. So again, conclusion. What is a conclusion? That existence of magnetic force depends on the frame of reference, depends on the point of view. In one frame of reference of A, magnetic force exists. In other frame of reference of B, magnetic force doesn't exist. Okay? And this is perfect example of relativity. Not only displacement, not only velocity, but also type of force is relative and depends on the observer, depends on the frame of reference. Okay? And this is a conclusion. Write this at the end of this lesson, that magnetic force or existence of magnetic force, or better, the nature of force, depends on the frame of reference. In one frame, in this case, in frame of A, magnetic force exists. In other frame, in this case, in the frame of observer B, magnetic force doesn't exist. So nature of force is relative. Okay, copy all to your notebook, read this 2-3 times, and learn this next lesson, some examples and some exercises, calculations related with this. Thank you for watching and see you next time. Bye!